Hi everyone, my name is Peter Shields and on behalf of EMF Scientific I'm pleased to welcome you all to today's webinar. We're fortunate to have Volker Brands, the Regional Sales Manager from Narda Safety Test Solutions in Germany, joining us today to present on 5G, new aspects and peculiarities for EMF testing. The development of 5G technology has seen new challenges arise for the field of safety and radiation monitoring. Today, Volker will go over the basics of 5G technology and the evolution of radiation monitoring in the 5G era. We've also scheduled another webinar as part 2 of this series with Volker presenting on Thursday the 8th of August, which will be about extrapolation to actual maximum exposure. So I hope some of you will be able to join us for that as well. So over to you, Volker.
So, as Peter already pointed out, there will be 2 parts. Today, the part will be introduction and basics about the new aspects and peculiarities of EMF testing. And then in August 8th, there will be the second part where we will dive a little bit more into the depth with regards to calculation and extrapolation methods to maximum EMF exposure. So what is the meaning of 5G? It is just short for 5th generation of cellular mobile communication system based on a standard which the association 3GPP is defining. It's also called new radio. New radio is also the differentiator to the name TM. There's also telecommunication management, the telecommunication forum defining another standard which is already heavily used in the US for millimeter waves. So basically there are 2 standards, the international one and the US American flavor, which we will not discuss today. So the history is starting with 2G, then we had 3G as the 3rd generation. Currently, most of the worldwide networks are based on 4G LTE with 2 flavors, frequency division and time division, FDD and TDD. And the new upcoming standard, which is just being now in trial and introduction phase, is the 5th generation. One of the big differences is the downlink data rate. You see starting with around 10 kilobit per second to 38 for around 400. Then with LTE, theoretical maximum was already around 150 megabyte, and now within a cell, there's a downlink data rate of 10 gigabit per second possible. Another big difference is the latency, which came down from some 100 millisecond down to 30 millisecond, which is now in the best case 1 millisecond. That means latency is important for services like IoT, Industrial Internet of Things, where you have telemetry signals, or where you need to have a very fast and quick response between actors or detectors. Think of automotive, of autonomous driving, where you cannot allow long latencies, which we have seen in the past systems. So the application is getting broader and broader. We started with voice, data, SMS in the 2G case. The UMTS already offered access to the internet. With the 4G, we came into what is called fast mobile internet. And now with the 5th generation, there is a vast amount of functions and applications like enabling, as I already said, the Internet of Things, car-to-car communication, broadcasting, ultra reliable and low latency, massive machine type of communications. So especially here in Germany, we also see a lot of introduction in industrial areas in big industrial plants. So it's not only the good old telephony, which is based on 5G, but also a lot of interconnection between machines. The last line maybe is important, that the propagation or the transmission of the signal was in the past mainly SISO, single input, single output. We have seen a few MIMO. So with 2G, there was already co- and cross-polarized antennas. dipole antennas with 90 degrees in between their two propagation lanes. With LTE already, few of the latest LTE implementation we have seen already beamforming, and with 5G now there's massive MIMO, and beamforming will be probably the standard implementation. Having a look in the frequency domain, where GSM was still based on single channels, single carriers, they were basically replacing if each channel was more or less emulating like a fixed line, a fixed connection, even though wireless, but a point-to-point connection in downlink and uplink. So even though there was the possibility of frequency hopping, basically was like that every user was having its individual channel. Then with 3G, there was the introduction of digital modulation. So in a channel, which was now not only 200 kilohertz, but 5 megahertz bandwidth, in this band, there were several channels in uplink and downlink. So there was a multiple use of this shared channel. In 4G, the maximum was then increased to 20 megahertz bandwidth, and now with the 5G for the lower frequency range, the bandwidth is can go up to 100 megahertz. Though I've just checked yesterday the licenses here in Germany, there are still licenses in the range of 5 megahertz, 10 megahertz, and 20 megahertz. So there is no license, for example, in Germany for 100 megahertz. So this is more the maximum possible implementation frequency band. Talking a little bit of beamforming and massive MIMO. What is that exactly? There was already a multiple input, multiple output of antenna arrays in modern Wi-Fi routers, and also even in some 4G installations. But so far it was only used to either to double transmit a signal, so to increase the quality, or to double the capacity by sending other signals over more than one antenna. But on top of this MIMO for diversity, there is now also the function of beamforming, which is being added, so that by electronic forming of the beams, it is possible to send more power, more energy to a certain position in space to have a kind of spatial multiplexing. So that was MIMO, which already was used since the 2G era. As I told you, co and cross polarized dipole. So a lot of individual small antennas, which allowed for a better direction of or directional beam forming of antennas. But this was all steady, and this was all static. It was not dynamic. So now we want to discuss a little bit the different cases of possible operational situations with 5G beamforming. One is first of all to have no beamforming, so that is the good old standard 120-degree antenna segment. And on the right hand, you see already the horizontal pattern of a segment antenna with beamforming. So if only two user equipments are active, then you have two very selective beams, which are only supplying RF power to these two user equipments. Then we need to differentiate it to different cases. There is the synchronization of signalization signals, and it's possible, for example, to have this in a scanning mode, so in a dynamic mode, so that in each 120-degree sector, the signalization signal is scanning mainly for detection, communication with the mobile phones, and to make sure that they're getting synchronized, that they detect the cell, and so on. At the same time, you can have fixed traffic signal on the right hand. So the blue beams show the user equipment with the uplink and downlink, get the optimum connectivity. So there are two different beamformings which we need to keep in mind. There's a horizontal scanning, so we're looking now from the top on the tower, on the rooftop, and we have the vertical scanning. So we're looking on the building on the right hand. Excuse me. And you see that there is also the vertical scanning component. So we have beamforming in two directions and in two dimensions. And now we need to again separate different cases. There can be the good old case that signalization and tracking is without beamforming. So that was the case in 2G, 3G, majority of 4G installations. Now with UMTS, it's possible to have signalization without beamforming. So the synchronization signals are being transmitted broadly, but the traffic is with the beamforming option. And or the most enhanced, the most sophisticated way of communication is signalization with beamforming and traffic with beamforming. So the latter case, or the case 3 on the right hand of the slide, could most likely be the standard case after all radio links, all radio stations have been upgraded to the latest and greatest software and hardware functions. We will see a lot of other installations like the first one and the second one for the upcoming time. But the target is to make the best use out of the technology, and that would be pretty much the situation on the right hand of the slide. Coming now to the subject of Narda, of testing. What does that mean for measurement of electromagnetic fields? So first of all, start with the personal protection at the workplace. So here the testers like the good old Narda Redman, or the new latest the Narda Redman 2, or the Narda Alert S3, or the NBM, the broadband meter, which is all being manufactured here at our German facilities. Modulation, crest factor, and signal shape are not critical to those instruments, so they will give you the right and the correct test result wherever you are and wherever you are positioned and whenever you're measuring. As 5G will also use frequencies above 24 gigahertz with really relevant output power. We of course need to focus now on models which are not limited to frequencies of 6 or 8 gigahertz, which was in the past sufficient. But if you want to have a future-proof solution, then of course you should make sure that you acquire respective models which have frequencies minimum up to 30, 40, better 60 gigahertz, so that your investment is future-proof. As the beam can change its directions, of course, necessary that the personal monitor should always be worn on the body, because only if it's worn on the body, here the new model Redman 2, you can make sure that body reflection is addressed in a correct manner, by help of the reflective of the attenuation foam, which we are using in the fixture of the Redman on your body. Definition of safety zones is of course still an ongoing task. So there are basically three ways to do this. You can do a rough estimation by calculation. So you start with the EIRP, so with the emitted isotropic radiated power. You use some approximations and calculations with the antennas, but that is quite rough because it's not taking into consideration the real situation on a tower, on a rooftop, with the path propagations, with the reflections, and so on. More precise is a simulation by a respective software, which we also selling the electromagnetic field calculation software 400 TC. Here's a little picture which allows a more realistic simulation. So basically, it's the solution of the Maxwell equation. So it's a correct mathematical calculation and approximation of the reality. Last but not least, measurements are giving ultimately the only true and only real information about the exposure at a certain time and at a certain position. And for this measurement, there is an extrapolation possible to actual maximum, where Narda has proposed two measurement procedures based on the selective radiation meter, the SRM 3006. So there are two measurements. One measurement is in frequency and time domain. We will touch that briefly today, and we will discuss this more into detail on part 2 of that presentation on August. So there are two possibilities to do an extrapolation. One is based in frequency and time domain. Frequency domain, the measurement; in time domain, you do some checks. So for that, it's necessary to have the scope mode, that is an oscilloscopic mode. Technically, it's IQ streaming in real time. It's a level meter in time domain. So a demodulation of the baseband. You see the whole baseband like on an oscilloscope, demodulated on a spectrum analyzer, to check the uplink and downlink to see if there is any effects of mobile phones in the uplink, which would corrupt the test result in the downlink. And the second method is a code selective method, which we are proposing. The first one is available right now. The second one is not available as per today, because the standardization has not been finished so far. Mainly IEC is working on that. But when the standardization is being finalized, then we will very fast look into a solution. Talking about solutions, what we are planning for next year is to have a down converter with the SRM 3006. That means a kind of horn receiving antenna, which will be addressing the higher frequency range of 5G. And so in that antenna will be a down converter, so that the millimeter wave frequency range will be down converted to the down to the 6 gigahertz range, which SRM 3006 can handle. And by help of the antenna control interface, this down converter and this antenna, this active antenna down converter will be powered by the SRM, and by the antenna control also the frequency range will be correspondingly correctly being shown in the SRM 3006. So that is on the roadmap. And secondly, on the roadmap, we're just discussing now the demodulation method for 5G, so that you really can also extrapolate to the actual maximum in complex situations where you have beamforming for the synchronization signalization part, and where you have beamforming for the user channels. To measure the current exposure, so not doing the approximation to the maximum, to measure the current exposure, and in a lot of trials and pilots now, you can set the system also to maximum exposure. So in that case, you will have the special situation that the current exposure is the maximum exposure. There are the NBM broadband test equipment is available, which you see here on the picture on the right hand. The latest probes cover signals up to 90 gigahertz. So in that respect, nearly all of the 5G implementation where you can think of are being included. The Narda broadband meter is able to measure the current field strength and presents the results either or in volt per meters, milliwatt per square centimeters, or directly in percentage of the standard of the limit curves. The selective radiation meter 3006 can perform, as the name says, selective measurements up to 6 gigahertz, and it can also differentiate and distinguish between the different services. And as I already pointed out, we are foreseeing extensions to frequency above 24 gigahertz. For integration over frequency, or what is called safety evaluation method, it's possible even to capture the power in services which are broader than the 20 megahertz resolution bandwidth which the spectrum analyzer is offering. So what you're doing, even though you use a resolution bandwidth of 20 megahertz, it is possible to scan over wider bandwidth, for example, 100 megahertz, and you define the lower frequency 3.5 gigahertz, the upper frequency 3.6 gigahertz. So now you're sweeping with the resolution bandwidth of 20 megahertz. Technically, these are FFT scans with overlapping fast Fourier transform windows. With overlapping, you scan through, or in the past it was sweeping in the analog world where we had analog test and measurement equipment. Now it's scanning, it's digitally. So you scan or sweep over the 100 megahertz with 20 megahertz and measure the current exposure. So you define this table on your PC, upload it in the spectrum analyzer, and then you see the result. Here it's a condensed view, so you can also have a detailed view. And in the index 1, you have the 5G service with the instantaneous value of 8 millivolts per meters, the maximum of 12 millivolts per meters, and the average of 9 millivolts per meters. You can also see that take a look on that with all the adjacent services, like in Germany we have, for example, GSM railway, so the 2G flavor for the railways. You can have decked phones in your vicinity. You have UMTS TDD, UMTS FDD. Maybe you have a Wi-Fi. You have the industry and science medicine band, so whatever signals in the non-licensed band, and then the 5G, the new services here, and then the instrument will give you the max value, the average value, other contributors which are so there is a kind of broadband measurement where you check for the gaps in the bands which are not contained in the upper list here, and then you get a total. And as I already explained before, you can have the presentation here in volt per meters in field strength, or in power density in watts, or you can have it directly in percentage of the limit which you have selected. For example, the ECNIF, the INCRMP value. Another approach to assess the exposure in the vicinity of towers and transmitter stations is a 24/7 measurement. Of course, measurement with the Redman, the NBN, the SRM is of course only a spot measurement in time. But if you are interested in 24/7, so continuous measurement, for that application, we are providing area monitor probes. We have two models: the broadband probe, the area monitor B, and the selective one, the area monitor S. And here we can again measure up to 40 gigahertz broadband. So that is good if you want to have a complete assessment of all signals. Of course, as a broadband measurement, you will also have, of course, broadcast measurements or radar signals in the vicinity of a tower included in this test results. Or we also have this selective one up to 6 gigahertz, and with this one, of course, you can select only the band for the 5G installation, and you only analyze this service on its own. In quite a lot of countries, these autonomous test stations have been brought out. So they are, as you see here, they are solar powered, and they come with a typically with a 3G modem. Other means of data transfer are also possible, RS-232 or via the Ethernet, and they they load up the test results on a database. And if this is being offered to the public, as in many countries, like in Italy, in this example is the National Observatory of Electromagnetic Fields in Greece, from the Greek Atomic Energy Commission, which is the radiation department for ionized and non-ionized radiation in Athens, in Greece. So here are hundreds of these stations brought out over the whole country, and every citizen can look up what is the exposure over the last hours, the last months, the last weeks. Even you can have a look up what is the exposure at a kindergarten where your children are, or what is the exposure in an elderly home where your parents are. So this is being installed in quite some countries, especially also in Eastern Europe, in Serbia, in south of Europe, in Italy. There are quite some governments which have brought out this monitoring. So like you monitor other environmental things like dust or like ozone in the atmosphere. People can see also the electrosmog, the pollution or load for humans. Coming to the last slides of today's presentation, and that is already slowly leading into the next part of this presentation, is the environmental measurement with the possibility to calculate the actual maximum exposure. So as the transmitted power of 5G and our base station depends strongly on the current traffic load and the user behavior, what we discussed before on the vertical and horizontal beams, of course, that means it takes a little bit more of consideration and a little bit more of efforts to correctly measure this. Yeah, so it means in practice that the current exposure method within specific observation time could be much lower than the actual maximum exposure. For that, many regulators enforce the extrapolation to maximum load as the measurement of choice, and to compare this result versus international or national or local limits. So in Europe, we have some municipalities which have their own limits, like the city of Brussels, or also nearby here the city of Tübingen, having even their city limits, the municipal limits, and this check can be assured that these limits being fulfilled and not exceeded with the maximum exposure calculation. Second last slide. Today, NASA started to discuss. NADA is proposing two methods to extrapolate to actual maximum exposure with the SRM 3006. Both these methods are based on measurement of signal components inside the signalization or synchronization signal blocks, which are independent from or independent of the current load of the base station. So this is like we had in 2G a beacon or a pilot, so signal where you know the power which you can use to calculate and extrapolate to the maximum of the field strength in the whole signal. With 3G, 4G, 5G is more complex because it is a quite complex modulation scheme. So either or you need to demodulate, that is the second method, or you have a look in the frequency domain, check for this signal resource block, and out of this signal resource block you identify this maximum. It is still easy now in the cases of trials and pilots where you don't have so many user equipment in place, and where you still see very clearly what is the maximum signal in the frequency band. But it will be quite more complex if you do measurements then in a couple of years where you can expect then thousands of mobile phones or internet IoT components which are transmitting and receiving. Again, both methods are based on measurement of signal components inside the signalization block, being independent from the current load of the base station. This measurement result can be used then to extrapolate to the actual maximum exposure. The first method is based on frequency selective measurement and a check in time domain. So you use both. You use the spectrum analysis function of a radiation meter, and you use the level meter and the oscilloscopic presentation to just have a logical check that you don't have too much of uplinks. Means mobile phones, for example, on the rooftop itself, which would corrupt the test result. First method, based on frequency selective measurement, is already being established for LTE signals. So there was already an ISC recommendation stipulating this measurement. And the second method is called demodulation-based extrapolation. So we already had that in the SRM for many years for 3G. We have that for quite some time now for 4G, for both flavors of 4G, the TDD and the FDD, the time domain and the time division and the frequency division method of 4G LTE. And the May edition of the Journal of Health Physics, my colleague Helmut Keller from our R&D department, he submitted a proposal and he described a method for 5G demodulation and decode-based calculation of or measurement of these signals in the signalization part, the primary and the secondary sync signal, and to use this for calculation to maximum exposure. If you want to have a look already on that paper, it's publicly available here. AirMet will submit this part of my presentation to all of you, and the hyperlink to that publication is included. More I will tell you in the second part of this 3G, this 5G lecture on August, same place, same time. And as this method is not being rectified by the respective standardization bodies, which is namely IEC and or ITUT, as long as the approval is pending. Of course, we will not start with the implementation because that of course costs quite some software design power. So we are still waiting for the finalization of that method, and then we're also planning to put that on the roadmap of SRM, as we have already started now with the first check for the millimeter wave application with SRM 3006. Okay, over to Peter, over to Melbourne, from Stuttgart to Melbourne.
Thanks, Volker. Yeah, we have got a few questions here. The first question, Volker, is what frequencies does Radman2 test up to?
Yeah, we have two for the Radman2. We have two versions. The Radman LT, the light version, and then we have the Radman 2 XT, the extended version. It's early in the morning. If I remember correctly, the LT version goes up to 6 or 8 gigahertz. Correct me if I'm wrong, Peter.
Yeah.
It's 8, huh? And the XT version goes up to 60 gigahertz.
Yeah.
And then for those special cases where you have radar signals which are even higher than that, then we have we also have the Narda alert, which is using a different sensor technology. It's using a TC elements, thermocouple elements, and they can even go and pick up signals up to 100 gigahertz. And the NBM, the latest probe is the 90 gigahertz probe, which is again using the same sensor like Redman, which is dipole diodes, yeah. And this NBM can reach up to 90 gigahertz.
Another question, Volker, fairly broad. Is 5G safe?
Is 5G safe? That is a big question. 5G is safe and unsafe as all the other technologies, and it's pretty much depending on the situation. First of all, it's all about distance. The closer you come to any antenna, the unsafer the situation will be. I've seen in Scandinavia, I've seen a few implementations where you have 1 kilowatt of power for a 5G station, which is pretty much. And if there are constant beams on you and you do a long download, then of course the exposure is much higher than if you are just in broadband beams and signalization and synchronization beams. I think the good thing about this beamforming is the user has it more now in its hands. If you want to be 100% safe, then don't use 2G, 3G, 4G, 5G mobile phones. And with the 5G, it's even the way that those who are heavy users will have more exposure. Those who are using sporadically or not using 5G at all will have much less exposure. So some colleagues already said that it's more democratic now, the 5G than the other flavors where you have a constant electro-smog noise around you. So safe and unsafe, we from testing, we can only tell you what is the level of exposure. The question safe, unsafe, of course, also includes people with other professional backgrounds like medical people, physicians, and not necessarily engineers only. So is it safer? Is it unsafer? Of course, the general tendency is that we have more and more signals in the ether. We have the frequency spectrum are getting more and more dense, but it's not only 5G. It is also uplinks and downlinks for satellites. It's also more broadcast signals. In Germany, we have now, for example, the good old FM radio in parallel with the DAB+. So the 100 megahertz band is full and crowded. The 200 megahertz band, the digital terrestrial radio is crowded. We have TV from many sources, not only cable TV and satellite TV, but also DVB-T. So also 700 megahertz is crowded. We have Tetra. The police communication, which is around 400 megahertz, also being crowded. We have now 2G, 3G, 4G, and 5G all in parallel. So I think it's necessary that organizations like the United Nations, with the World Health Organization, and with a sub-organization called ICNIRP or ICRNP, are looking into that and looking not only for the short-term effects, which we pretty much know, the heat effect. With radar, it's more complex because in radar you have these very short pulses and the very short signals with a vast amount of amplitude, but also that is being described in ICNIRP. You have the low frequency sensoric effects on bodies, yeah, induced currents in the body. So these are these three effects which are known, but these are all short-term effects. And the analysis and the checking of what is happening with the long-term effects is still ongoing. So future will tell us. That's probably, of course, not what you want to hear. But from my point of view, I cannot tell you what is. I think it's not a black and white, safe or unsafe. It's more like nutrition and like sports. I think it's a combination of all. If you eat more healthy food and do more sports, it's the likelihood or the probability that you live longer and better is there. But for individuals, the answer can also be quite negative. Despite of that, you can have serious illnesses, even if you look for that and strive for a good balance in life. So I think it's same with the electrosmog. It's the combination of all which may lead to more risk and less risk in life. You know. But that is just the answer of a poor engineer. Yeah. And as I told you, physicians and medical guys are also required to answer that complex question.
Thanks, Volker. I've got a few more questions here. Can the NBN display measurements in microwatts per meter squared?
Can the NBM display results in power density? Is that the question?
In microwatts
yes.
per meter square.
Yeah, we have this, you know, Peter, we have this perimeter, this glider, where we can compute, but of course you can also do this by calculation. So of course you can calculate. I think we don't have all these units there, but of course you can compute the one into the other. Yeah. So as long as it's power versus region, area, no matter if it's millimeter, micrometer square, you can calculate and compute the one into the other. Yeah. So basically, what these testers are measuring is what they measure is for the higher frequencies, typically volt per meters, and then in the far field. You can compute this into amps per meters. You can compute this into power density. So basically, you have volt per meters, amps per meters, and you have watts per square meter. This could be, of course, calculated from milli, micro, nano watts, and then to whatever square meter, square feet. Nano or centimeters to the square and so on. Yeah. Have a look at the data sheet. In the data sheet, we give you a list of what is directly selectable and accessible. The others needs to be calculated then by hand, or we have this glider, this perimeter, where you can calculate from one dimension to the other dimension.
Yeah, I've got some of those. So if someone wants one, I can price it. Got a few questions on the SRM 3006. So, what's the expected time frame for the RF down converter for the SRM 3006? And I suppose as part of that, there's also
I can only give you a rough time frame. It could be not before 6 months, and I would not expect later than 18 months. Right. So in that, we're lucky in 6 months, half a year. If we are struggling with some whatever kind of hurdles, they could be technical, they could be commercial, that the solutions are too expensive for the market. So maybe then we need to have a second or third try other suppliers for the down converters. But pretty much my personal expectation, but I cannot. I'm not the only guy, or I'm not the guy who's responsible for our roadmaps. I would pretty much think in the range of 6 months to maximum 18 months from today, then we have this down converter. And the same answer I would also provide you for the decoding for 5G for the frequency range 1 for the lower frequency range. But of course, this the trigger will be the finalization of the standardization, so that the standard is fixed. And from that point we can, and then of course we need to have a look for availability of our software development team, that they're not working, that they finish the work on other jobs, yeah, and then they can start with the implementation of that. It will be an implementation which is, yeah, we'll also discuss this a little bit more on the second part of the go more into detail with the second part of the lecture, how the implementation may look like. Yeah.
Yeah. Okay. Now there's a couple of other similar sort of questions. So will these options, the down converter and the demodulation option, be compatible with the current SRM 3006?
Yes. Yes. That is of course.
Yeah.
The design target. Yeah. That it's not necessary to buy other hardware than the down converter, and that the decoding of course is still running with the existing SRM 3006. Yeah.
Okay. Another question: are there additional protection PPE for people taking measurements?
Additional protection in which way?
Yeah, personal protective equipment for people actually taking measurements.
I think the best protection is the Redman 2, the XT version.
Yeah.
That is the best. It's not a protection, but it's an alarming device which gives you well in advance information about the radiation situation at your location. The Redman 2 is not only offering to go up to 60 gigahertz, it also has a fast mode. So instead of the integration, typical integration time, I think it's 1 second, can go down to 30 hertz.
Yeah, no, that's right.
1 second, I think, and then you can switch it to fast, I think, which is 30 milliseconds, if I remember correctly. So that even if you're in the vicinity of radar stations, so in Europe we have a few towers where you have a combination of DAB+, we have a combination at the same tower, you have weather radar stations. So that can be the case, that you're being even alarmed for that. Another measure I could think of is, of course, wearing protection suits. Yeah, protection suits with the metal grid on your body, which is reducing by whatever 10 dB plus minus 10 dB. It is reducing the exposure. This is then a real protection device, because not only alarming is effectively protecting you, but then of course it gets complex with the reading of your alarm device. You need to wear it then outside. There's the reflection is probably more complex with this metal grid than the reflection from the body. So then it becomes more complex how to interpret the reading of your Redman in that case.
Thanks. Now, I think this is the last one, unless anyone else has got it. I'm not sure whether how you'll be able to answer this one, but is it true that 5G will penetrate through the human body and is currently a weapon used by the US military?
Second part of the question I'm not aware of. But who knows? First part of the question was if the radiation is passing through the body. Yeah, that's of course the case, because people behind your body still can use mobile phones. Huh? So radiation, of course, is passing through the body. What I know, if you go back to the defense applications, there are of course defense applications which are using radiation as a weapon. Yeah, if you use extremely high power signals, and you pulse them in the right way, but then of course there's a probability if whatever vehicles flying, floating vehicles or whatever kind of vehicles, flying vehicles or driving vehicles can be stopped because they all have a lot of electronics, and if you destroy this electronics by an extreme strong pulse, then of course you can bring helicopters down and or air fighters down. So these developments are there, but here you really talk about much higher electromagnetic fields than which is used in telecommunication. But it's like with all things in life, if you take it to extreme, then everything like medicine or nutrition, everything of course can become a weapon if you misuse it and increase concentration, things like that.
Yeah. Okay, thanks, Volker. I think we better wrap it up there.
Okay.
Thanks everyone for attending today. If you have any further questions on the Narda product range or anything that was discussed today, please feel free to contact any of your AirMet representatives. As I've already mentioned, we've scheduled another webinar, part 2 of this series, that will be presented by Volker on Thursday the 8th of August at the same time, which is more about measurements, extrapolation to actual maximum exposures. So I hope any of you who are interested in that topic will join us. And finally, I'd just like to thank Volker for your time today.
Thanks for your time. Thanks for the invitation. Yeah, have a good day.
You too.